I'm real excited to share this presentation with you all today. This has been an ongoing project that I've been advancing with the Nature Conservancy's Invasive Species Advisory Committee over the past 2+ years now, evaluating the effects, the real and potential effects of forest pests and pathogens on carbon sequestration and storage by North America's forests. So I'm going to start out with, oh, my slides aren't advancing. Hold on one second. There we go. I'm going to really start out with the basics here. So as you all know, there is a process called the greenhouse effect, which is really a natural process that keeps our atmosphere regulated, protects us from solar radiation, and makes life inhabitable on Earth. In more recent years, that effect, that greenhouse effect, has been intensified by humans and become unnatural. And greenhouse gases such as carbon dioxide, methane, and nitrous oxide have been released in higher quantities into the atmosphere, trapping more solar radiation, allowing less to escape back into the atmosphere, and causing our global temperatures to warm. We also have this natural process, and I'm sure many of you have seen this from your days in chemistry classes in high school or college. This is photosynthesis. And we talk a lot about how photosynthesis produces a lot of the oxygen that we breathe and produces clean air for us. But we don't talk so much about how much carbon photosynthesis takes out of the atmosphere and sequesters and stores in plant material. And that's what I'm going to be focusing on today. So what do I mean by sequestration and storage? Sequestration really equates to productivity. And the productivity of plants is their ability to grow quickly, the number and diversity of species that are on the landscape, essentially how much energy they're utilizing and how much elements they're pulling in through photosynthesis. So for carbon and for oxygen production, plants produce that through productivity. Storage is really the ability of plants to store that carbon in their systems. So things like giant tree trunks in this redwood tree out west store a ton of carbon. And this is also done through grasslands and wetland systems as well. So biomass is the ability for plants to sequester and store carbon in their systems. So most recently, the Nature Conservancy has identified natural systems as one of the greatest opportunities to combat climate change. So this was a publication put out by one of our lead scientists, Bronson Griscom, in 2017, which identified reforestation, avoided forest conversion, and natural forest management as having the highest likelihood to sequester and store carbon to meet our 2030 climate reduction goals. And we call this natural climate solutions. And when we think of deforestation and conversion, our minds immediately go to things like this. Images from South America or Africa where the Amazon rainforest is being cut down, developing countries where urban sprawl is changing natural systems into agriculture or pavement. And you would be right. Many of the major deforestation events and conversion events that are happening globally are happening in these places. And most recently, there was analysis conducted in 2017 that found that every second in 2017, we lost about a football pitch or a soccer field's worth of forest across the globe. And that equates to about an area the size of New York City every month and an area the size of Italy every year. So global deforestation is on an upward trend, jeopardizing efforts to tackle climate change and contributing to the massive declines in wildlife across the globe. We also need to realize this is happening in New York. So these are two maps showing the changes to impervious surfaces from 2001 to 2011 on the left in New York State, as well as the increases in housing units from 2000 to 2013 on the right. So even New York is not immune to losses of forest and conversion. We also have something else going on, which I'm going to be focusing on today. We have many forest pests and pathogens that are already here that are native. We have ones that are invasive that are here and causing significant impacts, and we have many more on the way. And these are quickly removing trees and killing trees in abundance across landscapes. We need to realize this is not a new phenomenon. This has been happening for the past 150 years, and our forests are actually still recovering from major forest pest and pathogen events and logging that occurred over the past 2 centuries. So here's 2 examples. On the left, we have American chestnut, which has been essentially functionally extirpated from the landscape. These trees were absolutely massive and were able to sequester and store extremely large amounts of carbon. Similarly, for American elm, this was an abundant tree on the landscape, also grew to massive sizes. This one, called the Old Elm of New England, was about 400 years old when it was cut down, and people said that the entire community could be shaded under it. If you look at our forests today, there are still trees that grow to this size, but not nearly as many out there. And our forests are still very young in comparison to what they once were. So thinking about forest pests and pathogens, when a native forest pest and pathogen affects a forest, I want to kind of give you a sense of what happens in a natural state. So let's say this is one of our northeast forests, and we have a native pest or pathogen affect it. At the current state, productivity and biomass, which are indicated here on the left, are relatively constant. Once a native pest or pathogen comes in and takes out some of our weak or stressed trees, we may have slight reductions in productivity and biomass for a short period of time when that tree dies and succumbs to infestation, or sorry, to not infestation, but to native pest damage. But what quickly happens is, as that tree degrades, is reestablishment happens, regeneration of these remaining trees that are on the landscape. And productivity and biomass rebound quickly and can often increase beyond what was at the pre-attack levels, because that wood material that has been killed is still on the landscape. It's persisting on the landscape and will eventually be transferred to soil carbon. So we haven't seen any reduction in carbon here. And as those trees reach their full extent and height and become mature, we can have balanced productivity and biomass again. Now compare that with an invasive pest or pathogen. So similarly, at pre-attack levels, we're at a stable state. Now we have an invasive come in. The difference here is that when that tree dies, productivity goes down for a short period of time and biomass can remain relatively stable. But we don't have that species recolonizing on the landscape anymore. We have the remaining species that are there. So this is an example similar to Hemlock woolly Adelgid or emerald ash borer, where a pest is killing one single tree or genera of tree species on the landscape. So ultimately, the productivity and biomass of that forest in the future will depend on the productivity and maximum achieved biomass of those replacement tree species that are still there. Ash and hemlock might be gone, but things like maple and oak and other species are still there. And depending on what's going to replace them, that will determine what we have for productivity and biomass longer term. So let's look at an example of this. So Hemlock woolly Adelgid is a great case study. And if you look at the literature, there are really 3 different species that are called out as being the ones that will most likely replace hemlock as it's removed from the landscape. The first is rhododendron in the south. And if you think of a hemlock forest converting to rhododendron, most likely you would have higher productivity from this evergreen rhododendron, but you would have much less biomass. Rhododendron is not able to achieve the same level of biomass as hemlock is able to. What about black birch? Black birch will probably also have higher productivity, and probably have about the same level of biomass, maybe a little bit less. It's not able to grow as big as hemlock, but pretty close. So there's gives and takes here based on the species that recolonize. What about red maple? This is the one that is most referenced as replacing hemlock in the east. This one, productivity would most likely go up as well, but have you ever seen a red maple that grows as big as hemlock? I haven't. So biomass will likely go down longer term. Now let's look at another example. So the previous example focused on specialist pests like emerald ash borer and hemlock woolly adelgid. But what if we have a generalist pest come into the country, something like Asian longhorn beetle? In this instance, we have a broad suite of trees that are being impacted by this pest all at one time. And what happens here, you may start out with balanced levels, but as large numbers of trees die and decline across the landscape, productivity and biomass both go down. And you might still have some recruitment of those trees that are still on the landscape and not being affected by hemlock woolly adelgid or the generalist pest. But for several decades, you can have both productivity and biomass declining. And it's critical to know that when a forest transitions to reduced productivity and biomass, it switches from being a carbon sink to a carbon source. This is when our forests can actually be emitters of carbon into the atmosphere and make climate change even worse or facilitate climate change. And this has been documented in many instances in Canada through the interaction of native and invasive pests and pathogens. I'd encourage you to look at that work. So here's an example of that. This is work that came out of the Cary Institute of Ecosystem Studies by Dr. Charlie Canham. And what this graph shows is the total adult above ground biomass by trial run from 2000 to 2025 or 2500, where climate change and no pests and pathogens were modeled, climate change only was modeled, climate change plus emerald ash borer, hemlock woolly adelgid, and beech bark disease was modeled, climate change plus emerald ash borer, hemlock woolly adelgid, beech bark disease, and Asian longhorn beetle was modeled, and then climate change only with 6 degrees difference was modeled. And as you'll notice, it wasn't until the generalist pest, Asian longhorn beetle, was brought into the equation that we saw these significant reductions in biomass. So even if you have numerous forest pests and pathogens affecting the landscape, if they're specialists and they are fairly widespread apart as far as their introduction and spread, you usually won't see those reductions in biomass and productivity. It's not until you see a generalist pest that affects multiple species of trees where this becomes a real concern. However, there's another instance where we can have our forest transition from forest carbon sinks to sources. And that is when multiple forest pests come in a short period of time. So say we had hemlock woolly adelgid come in 1 year. A couple years later, we had something like emerald ash borer come in. A few years later, we had another forest pest and pathogen come in. This can also significantly change our forests into carbon sources because we're having the same effect, same aggregate effect as something like Asian longhorn beetle. The difference is the pace of introduction. If the pace of introduction of new forest pests and pathogens is rapid, our forests can become carbon sources. We also can't assume that when trees are removed from the landscape by a forest pest and pathogen that we're going to get significant or sufficient regeneration. In the face of interactive and synergistic effects like deer overabundance, invasive plants, and fire, sometimes forests do not come back or not in sufficient quantities. So say, for example, we had a forest that was affected by emerald ash borer, but the understory is all Japanese barberry, and that's limiting sufficient recruitment. That forest will likely persist in that state for a period of time and continue to be a carbon source instead of a sink because of the lack of sufficient tree regeneration. Similarly, if we have too many deer on the landscape, if that forest is killed and there are no seedlings being recruited into the understory, then that forest will continue to persist as a carbon source, carbon source. There's also this wrench that's being brought into the mix more recently in the form of catastrophic wildfires. So out west, when something like mountain pine beetle affects our forest over a large scale, we have increasing amounts of tinder being added to the landscape and spurring these massive wildfires. And in these instances, carbon is almost immediately released back into the atmosphere, and the soil carbon is lost. So this is kind of the worst case scenario where a forest pest and pathogen and fire disturbance regime are releasing extremely large amounts of carbon into the atmosphere in very short periods of time. So here's the situation nationally. I'm sure many of you have seen this map from Liebhold et al. In 2013, which shows the number of pests per county across the United States. As you'll see, New York is really a hotbed for the introduction of forest pests and pathogens, largely because we are an international trade hub. We have a lot of wood packing material coming into the country through the ports in the Great Lakes, New York City Harbor, and other mechanisms. And we are the bullseye, and from there, forest pests and pathogens spread across the rest of the country. And as far as current impacts that we're experiencing from these forest pests and pathogens, on an annual basis, forest pests and pathogens are impacting 20.4 million hectares in the US, an area almost 50 times larger than fire, with an economic impact nearly 5 times as great. The caveat here is this data came out in 2001 and does not account for the current catastrophic wildfires that we're experiencing. So if that were to be incorporated, definitely forest fire would be a more significant contributor to carbon than forest pests are now. And some of the resulting observed changes are larger in magnitude than those attributed to climate change or air pollution to date. And both native pests and pathogens and invasive pests and pathogens are expected to become more severe with climate change. What about projected impacts from current pests and pathogens? What can we expect into the future? Based on analysis, an additional 334 million hectares, or 63% of the nation's forest land, are at risk for increased mortality, and 24.8 million hectares are predicted to experience more than 20% loss of host tree basal area by 2027. And that was data that came out of the Cary Institute in 2016. Approximately 4.4 billion tan oak and oak trees containing approximately 295 megatons of carbon are at risk to sudden oak death in Oregon and California alone. And forests of Canada could emit between 30 and 245 megatons of carbon dioxide per year as just a result of native insect outbreaks. And we are also getting some new data on continental impacts. So most recently, there was analysis conducted by Seidel et al. That estimated the live carbon at risk from potential future invasions of 5 current forest pests as 1,027 teragrams of carbon with a recovery time of 34 years. So you can imagine if we're trying to meet our climate reduction goals by 2030 or 2050, and yet we're experiencing invasions that are causing our forest to recover for decades, we're just losing ground. We're not going to be able to meet our climate reduction goals if our forests have to go through that recovery time in order to sequester and store that amount of carbon and really harness the full potential of nature to combat climate change. Unfortunately, there has not been a comprehensive analysis conducted for North America, and that's what the Nature Conservancy and our Invasive Species Advisory Committee is working on currently. So we're currently in the process of submitting a publication in collaboration with the U.S. Forest Service, Purdue University, and the Cary Institute of Ecosystem Studies that gives a high-level summary of what we can expect in North America as a result of forest pests and pathogens and their effect on carbon storage and sequestration. We're hoping that research will spur additional interest in this topic, and that additional research will be conducted over the coming years to really get a holistic sense of what is at risk if we do nothing on this issue. We also need to ask if the rates of introduction are decreasing. So if it's really a matter of whether the pest is a generalist or whether the rate of establishment is increasing or at a rate that is not allowing our forest to recover in a sufficient amount of time, the question is, are the rates of introduction decreasing? And unfortunately, from all the literature that we've looked at, that is not the case. So this is the most widely cited paper on this topic from Alkema et al., 2010. And what they found is that over the past 200 years, the rate of introduction has been about, on average, 2.5 new pests and pathogens brought into the country each year. It's important to note that the number of wood-boring insects has been increasing faster than other taxa, coincident with the increased rates of international trade and transport of woodpacking material. And wood-boring insects and diseases have the most significant impacts on carbon storage and sequestration. Similarly, there was another paper by Liang et al. In 2014 that evaluated whether we maintain the status quo with ISPM 15. If you're not familiar with ISPM 15, this is the international standard for phytosanitary measures, which requires woodpacking material to be heat treated prior to being used for international trade and transport. So even with the current regulation that's in place, ISPM 15, they found that the number of new forest pests that could come into the country could increase from about 50 in 2003 to over 300 by 2050. So obviously what we're doing is not enough to curb the rate of introduction and protect our forests. Here's another paper by Boyd et al. In 2013, and this compared rates of introduction between the United States and Europe. So the green line here, the solid green line, line A, is the cumulative number of non-native insects introduced and found in association with trees to the United States during 1800 to 2006. And then line B here is the cumulative number of high-impact non-native tree insect pests and pathogens introduced to the United States during 1800 to 2006. So both are much higher than other countries, other continents, and are increasing. So you might be asking, why are we couching the forest pest and pathogen issue under a carbon story? There are a lot of other reasons why we should be worried about introduction and spread of forest pests and pathogens. And some of those reasons include they are the only recent forest disturbance agent that has proven capable of rendering entire species or genera of trees functionally extinct within a matter of decades. So things like American chestnut, American elm, ash, hemlock, if our efforts fail, these trees will be lost within our lifetimes, or already have been. And that's the only, forest pests and pathogens are the only forest disturbance agent that is capable of doing that. Several new pests now threaten to eliminate or sharply reduce the abundance and cover of other native trees and associated specialist species. So again, emerald ash borer and hemlock woolly adelgid are prime examples of that. And the short-term value of damage by 3 guilds of invasive forest pests is estimated to be about $150 million per year, with costs largely borne by homeowners and municipal governments. So when you have forest pests and pathogens affecting cities, there's really no choice but to cut those trees down when they die, and that comes with overwhelming costs. And even on the human health side, there have been documented instances of increased mortality and related to cardiovascular and lower respiratory tract illness in counties that have been infested by things like emerald ash borer. So from an ecological, economic, and societal perspective, forest pests and pathogens kind of hit all 3 nails on the head, in addition to contributing to losses of carbon. So hopefully at this point, you understand that this is an urgent need and an urgent issue that's affecting not only North America, but other countries and continents across the globe. And the question is, what can be done? So right now, the Nature Conservancy is really focused on promoting voluntary compliance and improvement measures for ISPM 15. We're currently in the process of advancing a new research project in collaboration with the U.S. Forest Service and APHIS that addresses the primary issues with ISPM 15 currently. And these include fraud, so people not complying with this standard and committing fraud to get their pallets into the market. Intentional undertreatment, so undertreating the pallets and not getting the full protection that is necessary in order to prevent forest pests and pathogens from being spread through international trade. Accidental or negligent undertreatment of pallets and wood packing material, and poorly or inconsistently constructed and applied ISPM labels. So the pilot project that we're looking to advance over the next 2 years will identify where we can make the most significant advancements across these issues and really promote voluntary compliance. So these are things like education and outreach at the supply chain level to inform them of what they need to be doing to ensure their pallets meet this standard. Potentially advancing an international wood packing material tracking system and database. There's currently no way to determine where a pallet came from and whether it's coming from a potential culprit country that could be spreading pests and pathogens at a higher level and rate than other countries. So we really need to bring the pallet industry and the pallet supply chain into the 21st century and make this a database that is easily searchable and trackable to determine where these pallets are going to and coming from. We need more corporate engagement on this issue. So the major suppliers or users of pallets and wood packing material is something we hope to engage on through our existing corporate partnerships with the Nature Conservancy. And we're also very excited about this non-compliance audit that's going to be identifying culprit countries. So currently the U.S. Forest Service is trying to identify if there are specific countries that are not meeting the ISPM standard more regularly than others and contributing to new introductions of forest pests and pathogens more regularly than others, so that we can target all of these other solutions that we have in mind. There's also some policy recommendations that are coming out of partner organizations like the Cary Institute of Ecosystem Studies. So this is the Tree Smart Trade, protecting environmental and economic benefits of U.S. forests, policy actions that Dr. Gary Lovett and others have worked on at the Cary Institute. And it really follows this SMART acronym. So the first is to switch to non-solid wood packaging material. And I will add that this is really most important in international trade. Domestic pallets and crates do not pose nearly as much of a risk as international wood packaging material. So really switching to non-solid wood packaging in international trade would significantly curb the introduction of forest pests and pathogens. Next is minimize the new pest outbreaks by expanding early detection and rapid response programs. A is augment international pest prevention programs with key trade partners. R is restrict or eliminate imports of live woody plants. And the thing I'll add here is it's really those plants that share a genera with one of the tree species that we have here in the United States. Those are the ones that pose the most risk of harboring a forest pest and pathogen that could be introduced here. And lastly, tightening enforcement of penalties for non-compliant shipments. So with that, I'm a little over time, so I'm going to go right to my last slide here. But as we think about the forests of the future, not only are they providing a lot of ecological, economic, and societal benefits, but we have to be thinking of them as these carbon sinks. This is one of the most critical benefits that they provide in the face of climate change. And in order to combat climate change and meet our climate reduction goals over the next several decades, we need to protect them and reduce the level of introduction and spread of forest pests and pathogens as much as possible. So with that, I'll end and I'll open it up to questions. Thank you.